If you guys could write down the question of the day, how can star clusters help us understand stellar evolution? What is a star cluster? It is a cluster of stars. It's a bunch of stars that are clustered together. We think that most stars actually form in clusters, and then over time, over millions and millions of years, stars will get slingshotted out of that cluster, and the cluster will slowly evaporate. However, if they don't evaporate, sometimes you're left with star clusters that last quite a long time. There are two types. The first one is a globular cluster. The second one is an open cluster. A globular cluster is a star cluster of hundreds of thousands, millions, tens of millions of stars that are clustered together. They're usually very, very old, and they are huge. An open Hello. Bye. An open cluster is much smaller, much younger, and they can be anywhere from a couple dozen up to a couple hundred stars. Take a second and write down the two different types of star clusters in your science journal. If I were to ask you which type of star cluster this is, or which type of star cluster this is, hopefully you'd be able to answer. Remember, a globular cluster is very old and contains up to millions and millions of stars. An open cluster is usually very young and contains a couple dozen to a couple hundred stars, which means this is a globular cluster and this one is an open cluster. Go ahead and take a second to draw a little picture representation of each type next to the definition that you just wrote down. In the constellation of the Toucan, there is a globular cluster called Globular Cluster 47 Tucana, and it's about 16,000 light years away from Earth. It's about 10.5 billion years old, which means it formed roughly the same time as our entire galaxy formed, and it's one of the brightest of the 150 or so globular clusters in our entire galaxy. When we zoom in on 47 Tucana, you can see that there are a lot of stars, not only in the visible light, but also in ultraviolet. You can see that there are some big blue stars, but there are much more red stars. Remember, as a star is dying, it turns red. So the more red you see, the older that star cluster is going to be. If you see a bunch of blue stars, that means it is a young star cluster. I just told you that this is about 10.5 billion years old, which means all of the extra gas and dust has already been used up. There cannot be any new star formation in this star cluster. But right here, we have a blue star. And big giant blue stars can only last maybe 10 million years at the most. So how could you possibly have a star that is 10 million years old in a globular cluster that's 10 billion years old? For the longest time, this was actually kind of a mystery. We could not figure out how that star could have gotten there, because there's no new material to make a star, and this star definitely is not very old if it's a big blue star. Turns out the only way to make a big giant blue star is if you take two smaller old stars and put them together. When you put them together, you take the mass of one star, add the mass of another star, and you're going to have a much bigger star. A bigger star means you move up on the spectral class from maybe an M-class star up to an O-class star, and you can have a new big giant blue star. The only way to get blue stars in these old globular clusters is star mergers, is stars running into each other. Let's say we were to live inside of this star cluster. We were to live right in the middle. Well, at the core of this star cluster, there's 130,000 stars with a magnitude of 6 or above. Remember, that's what you can see with your naked eye. Here on Earth, we can see maybe 5,000 stars if you have good eyesight. So if you look in the night sky, all of the stars that we see here on Earth, there's maybe 5,000 of them. You could see over 130,000 if you lived in the middle of a globular cluster. We'd have about 10,000 or so that are magnitude 1 or brighter. Here on Earth, we have 29. So take the 29 brightest stars, and you would have about 10,000 of those. There'd actually be well over 1,000 stars that are brighter than our brightest star. So our night sky would look very different. There'd be a lot more stars, a lot more bright stars, because they're so close. If we were to live kind of halfway between the center and the edge, our night sky would look something like this. the stars would be absolutely everywhere. However, if we lived at the center of this globular cluster, our night sky would look like this. There would be hardly any blackness in the night sky. There would be starlight everywhere you looked. Also remember that with this many stars, you can have supernovas, you can have gamma ray bursts, extra ionized radiation coming from all of these stars. It would be much less likely that life could develop on a planet orbiting a star in a globular cluster. It's because there's so many stars there. Which star cluster is older? M67 in Cancer or NGC 188 in Cepheus? And now for a very important point. It's known as the turnoff point. And the turnoff point is the point on the HR diagram where stars turn off their nuclear fusion and turn off of the main sequence. So there's two ways to think of it. If you turn off your hydrogen fusion and turn on helium fusion, that's the point where you start to swell and turn into a giant star. But it's also the point where you're no longer on the main sequence and you actually move up to the next little region of giants or supergiants. So the turnoff point is the point where a star turns off of the main sequence because it has turned off hydrogen fusion. Where do stars go after they turn off of the main sequence? They get big and red, to put it simply. Go ahead and write this down. Let's take a look at the HR diagram of a globular cluster, of all the stars in a specific globular cluster as time goes on. We're going to start at time equals 0, and the biggest of the big stars, the O-class stars, all the way down to about the G-class stars, are already on the main sequence doing hydrogen fusion. Some of the lower mass stars are still in the T-Tauri phase. They're still gathering in a bunch of material, so they're not on the main sequence just yet. Let's skip ahead to 10 million years, and you will see that every one of the O-class stars, the biggest of the big stars, has already started to swell up into its giant phase, and it goes over here to the right of the main sequence. This right here, this point, is what's known as the turnoff point. Some of the low mass stars are still not even fully formed, but the biggest of the big O-class stars have already turned off of the main sequence, and they are now in the giant phase of their life. From 10 million years up to 100 million years, now all of the O stars are gone, and some of the B stars have started to turn off of the main sequence. You now have all of your low mass stars on the main sequence, but you can see that the turnoff point went from here down to about here. Let's go from 100 million years to about a billion years. All of the O-class stars, all of the B-class stars have gone supernova, and now the A-class stars are starting to turn off of the main sequence and turn into red giants. And the turnoff point, you can tell, is traveling down the main sequence as time goes on. Move ahead to about 5 billion years. O-class stars are gone, B-class stars are gone, A-class stars are gone, and now you're starting to get F-class stars, maybe a few G-class stars turning off of the main sequence. They're running out of hydrogen in their core, and they're turning into a red giant. After 10 billion years, you're going to have the turnoff point all the way down here, about where the sun is, and the sun is going to start expanding out into a red giant phase. The sun is going to reach the turnoff point. And I want you to notice again, as time goes on, the turnoff point is traveling down this main sequence. The only stars that are left are the stars that last a very long time, the K stars, the M-class red dwarf stars. They're going to be here for hundreds of billions of years. Now let's go back to that question that I asked earlier between M67 and NGC 188. Which one is older? If you take a look at a plot of these two different star clusters, which one has the turnoff point farther down the main sequence? Well, the blue one has the turnoff point farther down, which means more time has gone on in the blue globular cluster. The farther down the main sequence you are, the older the globular cluster. So NGC 188 is much older than M67 because NGC 188 has the turnoff point farther down. The more red stars you see, the older it is. There's a whole lot more red stars in this, so this is an older star cluster. And in fact, NGC is much older, between 6 and 8 billion years old. Messier 67 is between 3 and 5 billion years old. So NGC, much older. NGC is going to have its turnoff point farther down the main sequence. If I were to ask you which star cluster is older, the Pleiades or M67, what would you say? What if I asked you what the youngest star cluster was? on this diagram? What if I asked you what the oldest star cluster was on this HR diagram? I want you to write these down real quick because you are going to need to know how old each of these clusters is for the next couple questions. I want to see if you guys can figure out which shape belongs to which star cluster. You are going to need the ages, so if you didn't write these down before, do so real quick. So which star cluster do you think belongs to the diamond? Well, the diamond has its turn-off point the farthest up, so it is going to be the youngest. Which one is the youngest? H and X Persei. Which one is the triangle? Well, the triangle has the turn-off point the next farthest down, so the triangle is the Pleiades. Then you have the X's, and the X's have their turn-off point a little bit farther down, so the X is the Hyades, which leaves, by process of elimination, the last one, NGC 188. That very old, ancient star cluster are the squares. Which one is older, M11 or M41? Which one is younger, NGC 752 or the Coma cluster? Now you guys have an exit ticket for this video. How and why would the HR diagram of an old star cluster appear different than the HR diagram of a young star cluster? Second question, explain why you think that figuring out the age of a star cluster could be helpful for astronomers. Finally, answer the question of the day, how can star clusters help us figure out stellar evolution?